Welcome to our webinar hosted by Shimadzu Scientific Instruments in collaboration with our partners across different countries in America. My name is Ruth Marfil Vega, and I'm the Senior Market Manager for the environmental market. I'm co-hosting today's event with my colleague, Alan Owens, and we will be presenting about pioneering new solutions for volatiles and semi-volatiles analysis. Before we start, I want to share a couple of notes for our viewers. The webinar console has a variety of items to help with your experience and interacting with us. In the screen, you'll see the following items. The slides will appear on the left-hand side. Directly under the slides, you will see a resource list with clickable links relevant to the material being presented today. On the top middle is the widget for questions and answers. Please submit your questions during the presentation through this widget, and we'll answer them during the Q&A session. Just below the Q&A box are the moderator and speaker bios. You may expand the items here to learn more about us. On the right are survey questions that you may fill out anytime during or after the presentation. Finally, at the bottom pane are the icons to bring up all these widgets in case they are minimized or hidden. With that being said, we have an information-packed webinar today, and we look forward to sharing it with you. So let's get started. I would like to reintroduce Alan Owens, the GC and GCMS product manager here at Shimadzu Scientific Instruments, who will be our main speaker today. Now, I'll hand it over to Alan.
Thank you, Ruth, for the introduction, and thank you to all of you for joining our webinar today. In this webinar, I will be presenting about the use of GCMS and GCMS-MS for the analysis of volatile and semi-volatile organic compounds. Our main focus today will be how the newest technologies from Shimadzu can help you to do the following: minimize sample reanalysis, accelerate one's method update and optimization, as well as how we can overall reduce your costs within the lab. There's a lot of information today to share with you, so let's go ahead and get started. Results and other information that will be shared during the following presentation were collected using different products in Shimadzu's lineup for GCMS single quad and GCMS triple quad. Starting with our GCMS QP2010SE, our high-throughput, robust workhorse production model. The GCMS QP2010SE is our entry-level single quad. Moving into our high-end single quad, the GCMS QP2020NX, this is our research quality and high-end single quad used for low-sensitivity applications. Furthermore, we move on to our triple quad series, our GCMS TQ8040NX and our TQ8050NX. The TQ8050NX is our high-end flagship model with the top-of-the-line performance and flexibility. Regardless of your application needs or budget, Shimadzu has the appropriate instrumentation for your needs. During the presentation, we'll be referring to several methods established by the U.S. Environmental Protection Agency, or EPA, for the analysis of VOCs and SVOCs. The table on the screen summarizes these methods with the corresponding number, the technology allowed by EPA for each of them, both single and triple quad, and the instruments we recommend for each application. For VOCs analysis, I would like to highlight that the EPA methods require the use of purge and trap for sample preparation and introduction. As for SVOCs, sample is introduced by conventional liquid injection after solvent extraction of the sample. Just briefly, all the methods with its different versions allow for the use of GCMS single quad at this time. The outliers being 8260 version D and 8270 version E, which do allow for the use of triple quad. I would also like to point out other contaminants that are listed in the far right column of the table, such as taste and odor, nitrosamines, 1,4-dioxane, as well as dioxins and certain PCBs. We do have the results to demonstrate the suitability of our GCTQ for the analysis of compounds such as the dioxins, pesticides, and PCBs. However, we won't have time to share this information in today's event. If you are interested in learning more about these applications, please don't hesitate to reach out to us or your local Shimadzu representative. Now that we've covered all of the different methods, both VOCs and SVOCs, let's focus on how we can do things like minimize sample reanalysis with our sustained stability. For sustained stability, what are we really talking about? Well, with VOC applications, we traditionally have something called a BFB tune. What is a BFB tune, you might ask? Well, BFB tuning is a spectrum check of 4-bromofluorobenzene, and it is used for the standardization of EI spectra to ensure our data reproducibility between both operators and different instrument platforms. Because GCMS systems may produce different mass spectra depending on optimized parameters and tuning protocols, which are typically manufacturer-based, BFB tuning is used to optimize the GCMS ion source optics to achieve comparable mass spectra across the different platforms. As you may be aware, the United States Environmental Protection Agency has very strict mass spectral criteria for its volatiles methods, including method 524 for drinking water and 624, wastewater. If an instrument doesn't pass the specified BFB tuning criteria, analysis of sample cannot be conducted. BFB is often checked at the beginning of each 12-hour work period. Unfortunately, these criteria were developed a long time ago on instruments that were nowhere near as sensitive as the modern-day GCMS. As a result, many BFB tunes on modern GCMS units are very unstable. Recently, Shimadzu enhanced its traditional tuning algorithm, which results in more stable spectra and response with newer released instruments, allowing you to maintain stability over longer periods of time. Here is an example of the stability of BFB tune on Shimadzu's GCMS single quads using the patented tuning algorithm. As you can see in the figure, we are monitoring the BFB stability in adherence to EPA 524.2 and tracking its stability over a series of injections. On the bottom of the figure, you will see the legend, as well as the sequence number labeled 1 through 25. On the far right-hand side, you will see the actual number of cumulative samples. As you can see within this image, we were able to maintain BFB stability upwards of 800 injections, which included both standards and samples. Regardless of the number of standards and samples, we were able to pass the daily BFB tune check without the need for any instrument maintenance or sample reanalysis. Although BFB tuning stability is of the extreme importance, we also wanted to measure the stability of our surrogates and internal standards. As you can see in the figure in the top left corner of your screen, again adhering to the same EPA method of 524, we tracked the surrogates and internal standards response over the same 800 samples. And even within a period of 800 samples with no instrument maintenance being performed or no sample reanalysis, we were able to maintain extreme stability for both surrogates and internal standards. We also plotted the stability of surrogates and internal standards for EPA 624 and 8260. In this study, we ran just over 450 samples. And in the graph here, you can see the standard response for all of the surrogates and internal standards within the method's criteria. Even with the 450 plus injections, we were able to maintain consistent and accurate results for an extended period of time, which confirmed the robustness not only of the tuning algorithm, but the instrument used in this application and study. Although the volatile methods for the EPA have been around for a long time, we decided to build pre-configured method packages specifically for these methods. These easy-to-use method packages for EPA methods 524, 624, and 8260 include all of the necessary standards as well as instrument consumables and even the labware to get started with your volatile methods. It also comes complete with vetted methods ensuring that you are successful with the most durable hardware on the market. It also includes the trusted BFB tuning algorithm that will keep your instrument up and running and your results consistent and accurate for extended periods of time. Following up sustained stability, we're now going to focus on how we can use Shimadzu's technology to accelerate one's method update or even its optimization. As we all know at this point, helium has become quite a scarcity, and those who can find it usually pay the price for it. This has addressed one of our most important critical needs for changes in the current methodology. There are several alternatives to helium being researched, specifically hydrogen and nitrogen. Both have their pros and cons, but even when using an alternative carrier gas, there are still things that need to be updated or optimized based on the differences between these gases and that of helium. What we'll cover here in the next few slides is how we can use Shimadzu to update or accelerate the update regardless of which carrier gas is being used. With alternative carrier gases, as I mentioned, there are pros and cons. But what are some of the challenges? Well, with alternative carrier gases, specifically with nitrogen, we need to make sure that we maintain proper GCMS operation. So with an optimized flow for both hydrogen and nitrogen, we need to make sure that we have enough vacuum to achieve the sensitivity required in the method. Our Shimadzu solution for this is the fact that, by default, our systems come with dual-stage turbomolecular pumps. These dual-stage turbomolecular pumps have the sufficient vacuum power to remove any excess hydrogen or nitrogen from the system, ensuring that we have the sensitivity needs to meet your limits. Although Shimadzu's GCMS and GCMS-MSs come equipped with turbomolecular pumps, and that we have the ability to maintain good vacuum, which leads to good sensitivity, the next challenge we face with alternative carrier gases is the ability to optimize the flow, whether it's for nitrogen or hydrogen. As I'm sure you all have seen the Van Deemter plot shown on the right-hand side, we understand that there are different optimized linear velocity ranges at which these alternative carrier gases are the most effective. Using Shimadzu's patented constant linear velocity setting in our software, we have the ability to maintain good chromatography regardless of which carrier gas you use. Along with features like ART, which we'll discuss a little bit later in the presentation, this will allow us to translate methods more easily as well as update our retention times to ensure our analytes never go unseen. Now that we've addressed the challenges that alternative carrier gases produce, let's talk about how we can accelerate our method's update or optimization, specifically with the ART function. Regardless of whether routine maintenance is performed on the column or the optimization for specific carrier gases requires an adjustment of retention times, it's imperative for users to quickly update method conditions to match the current instrument conditions. Shimadzu's ART, or Automatic Adjustment of Retention Times feature, does just that. Using an alkane standard, the ART function adjusts current retention times for targeted analytes using the retention time of inalkanes. Using the retention time of inalkanes allows adjustments based on linear retention indices, ensuring accurate retention times for target compounds across the entire analytical run. If we take a look at the typical workflow of the adjustment of retention times, there are only 3 simple steps involved in the process. First, the inalkane mixture provided by Shimadzu is run using the current method and instrument conditions. The alkane mix typically utilizes the retention indices starting with C8 or C9 up to C33 to adjust the method's retention times for target compounds, otherwise known as multi-point correction. By using multi-point correction, retention times are more accurately updated for all analytes, regardless of elution order/time. When compared to single-point correction, multi-point correction minimizes the differences in the adjusted retention time for all analytes. Once the retention times are identified, the ART function can be executed, which will then automatically update all of the retention times for the target compounds within the method. This tool ensures quick adjustment and accurate results anytime the instrument's parameters or conditions are changed. Now that we've updated the retention times, we can proceed forward with our analysis. In this example, we show the use of hydrogen carrier gas for VOCs analysis. In this study, we ran a mixture of 60 VOCs using the Megamix 30603 and diluted the calibration levels between 0.05 ppb and 10 ppb. Using our SH-RTX624 SIL-MS column, we were able to provide full separation of the VOC samples in less than 7 minutes. As you can see in the chromatograms on the left-hand side for vinyl chloride, dibromomethane, and tribromomethane, we were able to maintain sensitivity as the peaks shown are at 100 nanograms per liter using hydrogen as a carrier gas. On the right-hand side, we see a brief table showing the compound name as well as the R-squared values. I know it may be difficult to see, but most of the R-squared values are at 999 or greater. What we can show here is that within 7 minutes, we were able to drastically reduce the runtime using hydrogen as a carrier gas. We were also able to maintain not only sensitivity, but linearity as well. In this application example, we focus on the data provided by Criterion Labs running EPA 524.4, where nitrogen was used as a purge and a carrier gas for VOC analysis. As a quick highlight, we can see that the BFB tune passed without issues using nitrogen as a purge and a carrier gas. And using the same column, we were able to keep the same runtime using both helium and nitrogen. On the figure on the left, we look at specifically the QA criteria for the LRB and the LFB respectively, or the laboratory reagent blank and the laboratory fortified blank, to make sure that they were well within a passing range. For the LRB, we were looking at the non-detected up to 0.25 ppb, where the acceptable range for the LFB was 3.5 to 6.5 ppb. As you can see for the compounds displayed from vinyl chloride all the way to 1,2,4-trichlorobenzene, regardless of whether nitrogen or helium was used, the analytes or the concentrations reported were well within the acceptable range. Everything except for MB xylene was well within that target range of 3.5 to 6.5 ppb. As we continue looking at the results provided by Criterion Labs, we can see the MDL studies passed all criteria, with nitrogen as a purge and a carrier gas. The figure above shows the MDL in micrograms per liter for all of the compounds vinyl chloride through bromoform. All of the MDLs passed the criteria that was set to be less than or equal to 0.5 micrograms per liter, and were all less than 0.165 micrograms per liter. The results displayed excellent precision and accuracy observed with N equals 7 or 7 replicate samples, where the RSD was found to be less than 10%, and the recoveries within the 85 to 140% range. As we shift our focus to using hydrogen for SVOC analysis, we wanted to take a look at the DF-TPP tune criteria, specifically outlined in APA 8270D. As you can see in the example here, we show both the standard tuning criteria for PFTBA at the top left in helium and the top right with hydrogen. With the same tuning conditions, we were also able to run the DF-TPP tune check with both helium and hydrogen. One of the major things to note here is the lack of mass spectral pattern change. We were able to easily pass both DF-TPP in helium and in hydrogen. As for the results of using hydrogen as a carrier gas for SVOC analysis, we can see that the results proved consistent in terms of sensitivity, linearity, precision, and accuracy. In the table to the left, we see select compound names as well as their results for mean RRF, RSD, R values, or R squared values compared between hydrogen and helium carrier gas in terms of calibration results. For the precision and accuracy results, we also see the spiked amount, the mean recovery, and the RSDs for both hydrogen and helium carrier gas. Using hydrogen as an alternative carrier gas to helium provided these consistent results. As for the list of compounds, results from other targets in EPA 8270D are available in our application notes. Let's shift our focus to how we can reduce costs with newer technology, specifically GCMS triple quad, or GCMS-MS. In this upcoming section, we'll focus on the power behind triple quad and why this is now being allowed for certain EPA methodologies, and how you can benefit from this technology moving forward. In 2018, the EPA provided an update via SW846 that allowed GCMS-MS detector to be used for the analysis of SVOCs by EPA 8270E. The superior selectivity of GCMS-MS results and better sensitivity than that obtained with traditional single-quad GCMS. In addition to employing GCMS-MS for SVOC analysis, it is no longer required to use DFTPP analysis to provide verification of the system. The instrument's tuning parameters outlined by the manufacturer's spec now justify the use of this instrument for 8270E. For those of you who are unfamiliar with GCMS-MS, let's break down a little bit of the theory and some of the benefits. First, let's compare this to conventional GCMS single quad. In GCMS single quad, we have our ion source, our Q1, and our detector. As we expand to triple quad, we now have three quadruples, Q1, Q2, otherwise known as our collision cell, and Q3. Q1 and Q3 have the ability of mass separation, and Q2 works as an ion guidance between the first and the third stage. The basic function of Q1 and Q3 are the same as they are in single quad GCMS. In Q2, or the second stage of our triple quad, this works to collide ions after the first stage, which is why we call it our collision cell. The collision cell uses a gas to collide these ions, and what happens here is a collision-induced dissociation, or CID. There are several modes in GCMS-MS, but the most common is selected reaction monitoring, or MRM, multiple reaction monitoring. By monitoring multiple reactions, we have the ability to be more selective and in turn have more sensitivity. MRM has the ability to detect compounds because of its great selectivity. Even though the total amount of ions which traditionally reach the detector are less in triple quad than in single quad, we have the ability to detect peaks at lower levels due to this selectivity. As we can see in the figures shown on this slide, these mass chromatograms represent PCBs obtained in both SIM and MRM modes. In the SIM mode, some compounds are not detected due to the interference as well as the low sensitivity. On the other hand, the MRM shows good results by eliminating the impact of interference, which enables high sensitivity measurements with good repeatability. Although TQ has many benefits, method development for TQ or GCMS-MS methods can be difficult. We'll explain in a few slides how Shimadzu has a solution to simplify this method development. So far, we've talked about the quantitative abilities of GCMS-MS. Another benefit of using GCMS triple quad is the ability to run both SCAN and MRM in the same injection. In the bottom left-hand corner of the slide, we see a figure showing how SCAN and MRM events are set up concurrently, providing both MRM and SCAN data. On the right-hand side, we have the MRM transitions and the SCAN data shown above. This added benefit allows us to do quantitative work while also qualitatively confirming our peaks of interest. An added benefit of this as well is to perform unknown analysis in the same method as our quantitative method. As I mentioned before, if you're new to triple quad, the task of method creation and method optimization may seem daunting at first, but Shimadzu has tools available to eliminate that concern. The Smart Environmental Database contains over 600 compounds specific to environmental pollutants, and the database contains information such as collision energies, transitions, and retention times for said compounds. Utilizing this database, a GCMS-MS method can be created in 3 simple steps. ART analysis, can be used to adjust the retention times. We can then upload the ART file to the SMART database to create a method. And finally, we can move forward with analysis. Understandably, not all compounds of interest may be included in the database, as new compounds are added to watch lists frequently. Shimadzu also provides the MRM optimization tool with every TQ instrument, which contains methods and sequences for quickly adding new compounds to existing databases. For more information on the SMART databases and MRM optimization tool, please visit Shimadzu's GCMS homepage for how-to videos and additional resources. In this application example, we perform the analysis of SVOCs by EPA 8270E. On the left-hand side is a table of our GC and MS conditions. On the right-hand side, we see our compound list and a quick screenshot of our SMART environmental database. With the assistance of the SMART environmental database, we're able to go through and select specific compounds listed or outlined by 8270E with pre-developed retention indices, transitions, and collision energies to quickly output a GCMS-MS method. If there are additional compounds of interest that are not included in the existing database, there are commercially available libraries and other databases that we can include to accelerate method optimization when those new compounds need to be added. The quantitative results for the previously mentioned application are presented below. Out of the application, all 83 compounds passed guidance criteria outlined in EPA 8270E. Over 60% of the compounds presented percent RSD or RF less than or equal to 20%, and excellent linearity with wide calibration ranges, outlined here in the green, from 0.01 to 50 ppm and 0.01 to 20 ppm. An example of the calibration curve for asanaptine is shown below, as well as the percent difference of each calibration point. Here's an additional look at some quantitative results for some of the more challenging compounds, in this case specifically benzoic acid. As I mentioned before, all 83 compounds passed the guidance criteria outlined in 8270E, especially for these challenging compounds like benzoic acid and the nitro group containing compounds. From 0.2 to 50 ppm, we were able to pass with a quadratic fitting, and you can also see the percent differential of each calibration point shown below. Not only did we pass all of the guidance criteria outlined in 8270E, we also wanted to focus on the sensitivity at the lowest point of the calibration curve, or lower points in the calibration curve. As shown here, we have 1,3-dichlorobenzene, diphenylamine, and pyrene at 10 ppb. With 6 repeat injections, we were able to obtain very good peak shape, as well as low RSDs, 3.39 for dichlorobenzene, 4.20 for diphenylamine, and 3.96 for pyrene. As we mentioned before, not all compounds behave properly. In specific, 2-nitrophenol and 2-nitroaniline are some of the more challenging compounds for 8270E, but here we show them at 20 ppb with, again, 6 repeat injections with RSD of 19.67, and for the nitroaniline, percent RSD of 12.39%. For additional information or for additional quantitative results on the entire list of 8270E, or at least for the 83 compounds that we ran in this study, these are all outlined and displayed in the application note highlighted below at the additional results of our TQ8040NX application note. As I had mentioned in a previous slide, one of the major benefits of GCMS triple quad analysis is the ability to run a simultaneous or a concurrent scan MRM analysis. As we can see here, this scan MRM analysis supports our unknown compound identification. In the chromatogram in the middle, we see 2 analyte peaks designated by the gray text and the gray arrows. Just to the right of those 2 desired analyte peaks, we see an unknown peak near the 2 analyte peaks of interest. Because we have done a scan and MRM simultaneous analysis, we have the ability to library search that unknown and positively identify it as an amide peak. With scan-MRM analysis, we have the added benefit of superior quantitative analysis due to the selectivity of the triple quad, but also have the power to do unknown identification due to the scan data that is also collected. In conclusion, our advanced tuning algorithm, in combination with our rugged GCMS, ensures long-term stability for analyses of VOCs. We have also been able to demonstrate that even with the use of alternative carrier gases, we can have robust performance and enhanced sensitivity for both VOCs and SVOCs. With the update in 2018, the GCMS-MS or GCMS triple quad is now a vetted system for SVOC analysis, specifically with APA 8270E. And the added benefit of having a GCMS-MS is the ability to do simultaneous quantitation of target analytes and the qualification for unknown compounds. We appreciate your time and we appreciate your attendance. Before we let you go or answer any questions, I did want to point out our limited time offer, our extended warranty program. It's currently set to expire in the end of September 2023, and we are offering an extended warranty on the electron multiplier assembly for our current GCMS models. Yes, that includes both single quads and both triple quads. With this extended warranty, you get an additional 6 years after the 1-year factory warranty on all electron multiplier assemblies for main units. If you have any questions or are looking to see more information on the details of the extended warranty, please don't hesitate to reach out or contact your local salesperson for more information. And with that, I will pass it back over to Ruth.
Thank you, Alan, for your wonderful presentation. Before opening it up for questions, a few reminders. On the screen, you can see Alan's and my email. Please feel free to reach out if you have any questions. Also, you can find the link to our website focused on environmental applications and our YouTube channel, where you can find plenty of useful resources. And now, I would like to open it up for questions from our chat. As a reminder, if we don't get to your question live, we will follow up via email to answer your questions directly.
Alrighty. Thank you so much, Ruth. I really appreciate your time and effort in setting up this webinar, including the help with the presentation. I also want to thank everyone for attending today. We appreciate your time and contribution, as well as the questions. And with that, we will get into some of the questions within the chat. As a reminder, again, if there are some questions that we don't get to, we will reach out to you post-webinar via email to answer any questions, comments, concerns that you might have. So with that, let's dive right into some of the questions. So for the first question I see here, if you are currently running an instrument with helium, how easy is it to convert to hydrogen? Well, one of the nice things about Shimadzu is out of the box it becomes ready, or it is ready to run with hydrogen as a carrier gas. There is no need to change any of the pipings, tubings, fittings, etc. Shimadzu's manufacture with stainless steel tubing, so there's no need to switch out for any of the copper tubing. So it becomes out of the box ready to immediately switch from helium over to hydrogen. We also have some really good internal documentation that's customer facing on a hydrogen getting started guide. This will walk you through all of the parts and pieces that you would need to potentially add to the system. That means filters, consumables, etc. Even our recommendation on hydrogen generators, as well as some method development tips and tricks for those of you who are new to hydrogen. We do have that, and I'll offer that to all of our customers. Alrighty, let's move on to the second question. Can you run additional compounds methods on the TQ, the GCMS TQ? Yes, of course. So obviously we showed in this presentation the GCMS TQ use for A270E specifically. However, we do have several different kind of method packages that allow you to incorporate different analytes of interest on the TQ. So if we're looking for pesticides, and I believe we even showed a slide here with some PCBs, we do have the ability to run additional compounds on the GCMS triple quad. I hope that answers the question. We also have a nice follow-up question. Can the SMART databases be used with single quad? Yes, absolutely. So we have a wide variety of SMART databases similar to the SMART environmental database that I mentioned in the presentation today. All of these databases are split up via market, but a lot of the databases that we do have in existence along with the environmental and the pesticides do have SIM ions built into the databases as well. So if you're not ready to make the jump over to triple quad, we do have SMART databases that will positively affect or help with method development, not only for triple quad, but for single quad as well. If you have a current existing instrument, like a single quad or a triple quad, a lot of these SMART databases can be added on at a later date as well. So as you're moving forward and having issues with method development, feel free to reach out to sales or some of the technical resources within the region, whether it be your tech support engineers or service engineers, to inquire about the compound list. So we will provide a compound list as well if you are inquiring about the compounds within the SMART databases, just to make sure that these databases do cover all of your needs. All right. And we have another question here as well. Are you able to reach the 8270 TACO limits in SIM or full scan? So currently the methods that we've run or the applications that we've run have been at minimum a SIM scan method, so a simultaneous scan and SIM method. We were easily able to meet the 8270 limits required using the SIM scan method. I don't see that we would have an issue with the full scan method meeting those limits. Having said that, though, that is not something that we have produced application-wise. That is absolutely something that we can look into and potentially run to test. But in terms of meeting the limits, we were able to do so with a SIM scan method. And then, of course, for 8270E, we were able to meet all of those limits with our TQ8040NX using an MRM method as well as an MRM scan method. Okay, and I see we have another question here. Have you had any issues with the N-nitroso dimethylamine integration? So we definitely haven't had, I wouldn't say, any issues with integration. That peak or that compound of interest that you had mentioned in the chat is one of the poor performers that we've noticed with the specific method. The detection limits as well are definitely not as low as some of your more traditional compounds or better performers, but we have not had any issues with integration. Currently what we have issues with is completing a full calibration curve. As people want to push lower and lower, there are just certain compounds like the N-nitroso that you mentioned here that just don't calibrate that low, regardless of whether we're using single quad or triple quad. So finding out the necessary calibration levels for that with the big detection limits. We do have some data on that specific compound that we would be more than happy to share with some external or additional application notes, but we can definitely reach out to you to determine what issues that you're currently having, if you're having issues, and provide some of the data and application notes that I'm referring to show exactly the chromatography that we see on our instruments at Shimadzu. Alrighty. And I see a follow-up question about that same compound, the N-nitroso dimethylamine. How have you increased the detection limit? So in terms of increasing the detection limit, one of the things that we've done, that compound specifically, along with a large number of the other nitro compounds, we've done some full method optimization studies with those. So trying to fine-tune as best as possible the transitions required for that specific compound or additional poor performers. And then on top of that, not only just the optimization in terms of collision energy, transitions, things like that, we've also tried to do an improvement on the resolution within the actual quads. So we have the ability to manually tune or manually adjust the resolution on the individual quadrupoles. So by manually adjusting or setting specific adjustments for the resolution on those quadrupoles, we've been able to boost the detection limit on the core performers. The other thing as well is we've tried a few different columns with different phases to ideally improve peak shape as well, making the peaks a little bit sharper and easier to detect. Within that optimization study, we've also kind of manually adjusted or manually increased or decreased the specific dwell time within that compound's range to try and improve more points across the peak. So the more points across the peak that we have, the better we are at actually forming repeatable quantitation. So even at those low limits and the detection limits down at the way bottom, we've tried to optimize individually for these specific compounds in certain applications. And I see another question in the chat. This session will be recorded. Yes, absolutely. So this entire presentation, along with the Q&A, will be recorded. It will be available for on demand. If you would like a copy of that, please don't hesitate to reach out. But in the additional resources with the applications, the slides, et cetera, all of those are available for download. And the recorded webinar, including this Q&A, are available for on demand. And then I see one more question as well, not necessarily related to VOCs and SVOCs for GCMS. I see a question about PFAS. I know we've done a lot of presentations and webinars in the past on PFAS, specifically including Ruth Marville-Vega, our Senior Marketing Manager for Environmental. I know she's done a lot of work on PFAS. I would suggest if you would like to find out more information on PFAS, please head to Shimadzu's website. In the Industries tab, there is an environmental page, and I believe there is a couple of dedicated pages specifically geared towards PFAS, both for LCMS and other techniques, with some webinar information as well as some booklet information on the current applications that we have for PFAS specifically. All right. I believe that is all of the questions that I see in the chat. If there's a few posted a little bit later, again, we will be sure to reach out to your specific questions if they were not answered via email at a later date. And finally, I want to thank everyone for attending. Again, we appreciate your contribution to the chat as well as your engagement with the presentation. If you have any questions moving forward with VOCs and SVOCs, specifically in regards to Shimadzu, please don't hesitate to reach out to myself, Alan Owens, or Ruth Marville-Vega via our emails, or reach out to your local sales representative, tech support representative, and we'd be more than happy to help fill you guys in on any questions that you may have. So with that, I will let everyone go, and I appreciate your time and hope you have a great rest of your week, and talk to you all soon. Thanks so much. Bye.